Here we're going to start looking at oxidation states for A-level chemistry. Now, it's quite hard to define exactly what's meant by oxidation states, so I'm going to explain it using two equations here. Now, in this first equation, we've got sodium atoms with one electron in their outer shell are unstable, so they lose that outer shell electron to form sodium ions. So, two sodium atoms in this equation lose 2 electrons in total to form 2 sodium ions. The chlorine molecules here, they gain these 2 electrons lost by the sodiums, and that forms 2 chloride ions. So we've got two reactions. We've got an oxidation reaction, and we have oxidation is loss of electrons, and then we have a reduction reaction as the chlorine gains 2 electrons. So we have oxidation and reduction here for these two different reactions. Now, the oxidation states are the charges on the element here and the ions here. So our oxidation state is determined by the number of electrons either lost or gained. So our oxidation state here for the sodium is 0. It's now +1 in here because it's lost 1 electron. So each sodium loses 1 electron. Here our oxidation state of our chlorine is 0. And here our oxidation state of the chlorine is a chloride ion is -1 because it's gaining 2 electrons. So oxidation states change depending on whether elements and molecules gain or lose electrons. So those simple equations help us explain what we're talking about in terms of oxidation numbers. Now, what you need to be able to do for A-level chemistry is actually look at oxidation states in different compounds and look to see what has been oxidized and what has been reduced. Now, there are some general rules that you need to know about. So, first of all, group 1 elements will always have a +1 oxidation state. Now, there are some exceptions to this. You don't need to know about them for A-level chemistry. They are really obscure. Group 2 will be +2. Oxygen will be generally -2. Now, there are some exceptions. And these exceptions are in peroxides or when the oxygen is bonded to fluorine in F2 and O. So we will look at these exceptions, but these are the general rules so far. So -2 generally for oxygen, except for when it's in peroxide, such as hydrogen peroxide. Hydrogen would generally be +1. There are exceptions. Metal hydrides, where hydrogen will be a -1. This will be quite useful to understand because in the A2 part of the course, you'll look at hydrogen part of a compound where it will be a reducing agent. Fluorine is always -1. So those simple equations help us explain what is actually meant by oxidation and reduction and what we can actually refer to for oxidation states. Now, for A-level chemistry, what you're going to need to learn is some general rules of oxidation numbers so that you can apply them and you can work out oxidation states in different compounds. Now, these examples here are the general rules for different elements. So group 1 are generally +1, group 2 are generally +2, oxygen is generally -2, except when you find it in peroxides, we will look at later, it will not be -2 in a peroxide, or when it's bonded to fluorine. Hydrogen is generally +1, except in metal hydrides. And in that situation, hydrogen will actually be a negative charge, -1. Fluorine is always -1, and chlorine is generally -1, except when bonded to oxygen or fluorine. So in these situations, make sure you spell your fluorine correctly. So these are the general rules. there are some exceptions here, and it's really important that you get to know these kind of exceptions. Now, I wouldn't get too bogged down in them because it doesn't come up very often. These exceptions are quite rare that you'll actually find them, but it's certainly a good idea to have a fairly decent grasp of what is meant when we talk about general rules of oxidation states. So alongside those general rules of oxidation states, there are some other things that you need to be aware of. Now, the oxidation state of an element is 0. So if an element, if it's an element, so for example sodium atoms or oxygen molecules or hydrogen molecules, the oxidation state of that element will be 0. So my examples here, in hydrogen, the oxidation state is 0. If we've got chlorine, the oxidation state again is 0. If we have sulfur molecules, again the oxidation state is 0. If you have atoms like xenon, the oxidation state again is 0, or argon. In all these examples, these are all the elemental form. They have no charge. Their oxidation state is 0. Now, if the charge of a molecule is 0, so for example, HNO3, all of the oxidation states of these elements add up to an overall 0 charge for that molecule. So for nitric acid here, all of the oxidation states of these different elements adds up to 0. If you have an ion, so for example the ammonium ion, the oxidation state of these elements adds up to the charge of the molecule. So here with the ammonium ion, we have a positive charge, so the oxidation state of all of these elements added up must equal +1 for this particular example. If it was a negative ion, say a carbonate ion, CO3 2-, the oxidation state is going to add up all the elements, so the carbons, the oxygens, all added up, the oxidation state is 2- overall. The final thing to be aware of is that the most electronegative element so we're talking about oxygen and fluorine, so fluorine the most, and then oxygen, will always have a -1, not a -1 charge, sorry, a negative charge. However, just be careful, because remember the oxidation state, just be aware, so for example oxygen is -2. Remember, if oxygen is bonded to fluorine, then oxygen is not the most electronegative, therefore it won't have the negative charge in this situation. So if you go back to those general rules, oxygen's -2, but if bonded to fluorine, it's not. And that's because you've got to look at the fact that the most electronegative element is always the negative charge. So here we've got some different examples of compounds and ionic compounds. What we're going to do is work out the oxidation state of each of the different elements within these compounds. So we're going to use our general rules from the beginning of the video. We're going to start here in the top left and look at methane. So our general rule, hydrogen is always +1, except when it is in a metal hydride. This is not a metal hydride, so we know here that our hydrogen is going to be +1. There are 4 hydrogens, so in total that is 4 times +1. So in total that's +4 there for the hydrogens. So we would say that the oxidation state of the hydrogen in this particular compound is +1. Now that adds up to +4, so that the carbon must be -4 overall to make 0, because methane has no overall charge. Having a look at the next one, so the silicon tetrafluoride, SiF4 here, we have a -1 charge for the fluorine, which we know, because fluorine is always -1. So that gives us -4 overall for all the fluorine. So that leaves us with +4 for the silicon here, because again, the silicon tetrafluoride has no overall charge. So we've got a slightly different one here. So we've got an ion in here with the ammonium ion. Now we know that hydrogen is +1 unless it's in a metal hydride. Again, this is not a metal hydride. So we have a +1 charge for the hydrogen. That all adds up to +4 in total because there are 4 hydrogens. Now the nitrogen here must therefore be -3 because it needs to add up to an overall charge of +1. So that's +4 for the hydrogens, take away 3, adds up to the +1 charge there for that hydrogen. The next example here, so we've got one of our exceptions to our rules this time, because we have hydrogen which is not bonded to a hydride, to a metal, sorry, so it must be +1 for the hydrogen. That means this is +1 times 2, so it's +2 overall for the hydrogen, so it's +2 in total for all the hydrogens in there. Because this has no overall charge, that means that the 2 oxygens together have to make -2 overall. So the oxidation state of the oxygens must therefore each be -1 to give you -2 overall for those 2 oxygens, and that gives us no overall charge because +2 for both the hydrogens, -2 for both the oxygens is 0 charge overall, leaving us with an oxidation state of -1 for each oxygen and +1 for the hydrogen. This next example in sulfuric acid, here we don't have any exceptions to our rule. So the ones that we know, we've got +1 for the hydrogens. So in total, that's +2. The sulfur we're not sure on because it's not one of our general rules, but the oxygen we do know is -2. So in total, -2 times 4 is -8 for all of the oxygens. The overall charge is 0, so -8 plus 2 is -6, so that means that the sulfur must be +6 in this particular example. So we must have +6 here for the sulfur to make that +6, take away 2, sorry, +6, take away 8 is -2, add 2 gives us 0 charge overall. This next example, Fe3O4, is a slightly tricky example. So we've got oxygen. It's not in our list of exceptions here. So we know this one. We know this is -2 for our oxygens. So in total, that's -8 overall. Because there are 4 oxygens times 2, that's -8. So from this, we have to somehow find +8 in total. So what that means is that our ions in here have different oxidation states. Now one of our ions in there is going to have an oxidation state of +2, and 2 of our ions are going to have oxidation states of +3. So there's 2 of +3, that's +6, add another 2 is +8, add that to this one, that gives us +8 in total for all of those ions in there. So we've got ions of different oxidation states within that particular compound. Don't worry too much about that example because it's unlikely you'll get that at A level. It's just one to be aware of just in case they do fancy asking something like that. Here we've got the nitrate ion, so we've got an overall charge of -1, which we're going to have to be aware of. But we have a -2 charge for the oxygens because it doesn't belong to any of our exceptions here. So that's -6 in total for the oxygens. -6. And that leaves us with the nitrogen needs to be +5 to make -1 overall. Next example, we've got oxygen again, not part of our exceptions. So -2, that's -6 overall. So we need to find +4 from the carbon for the overall charge to be 2-. Our last example here, now we've got some brackets. This doesn't really make this example any more challenging. It's just adding and subtracting again. So calcium is a group 2 metal. So there are no exceptions. It's always +2. That means that this whole hydroxide ion must be -1 overall. Now to make that, again, we have no exceptions in here because we have +1 for the hydrogen. We have -2 for the oxygen. So that is -2 + 1, that's -1 for each hydroxide, but we're timesing that by 2 to give us -2 overall. Add those two numbers together, and then there's no overall charge for our calcium hydroxide. So that's just a simple introduction into oxidation states. The next video is going to look at what happens in equations and how oxidation numbers change again. Now, it's not really any different. You look at the oxidation numbers and that helps you work out which elements have been oxidized and reduced in particular reactions. Thank you for watching. Please hit the like button, subscribe to the videos, and make sure you share them.